Today's topic is conformal mapping. Let a complex valued function w is equals to f of z. Then for each point z is equals to z0, we have a point w0 in the complex plane such that f of z0 is equals to w0. Now let z is equals to x plus iy. And w is equals to f of z, that is equals to u plus iv. Then u is equals to u of xy and v is equals to v of xy, which represents a mapping which establishes a correspondence between the points xy in xy plane, that is z plane, and the points uv in uv plane, that is w plane. Here, using this above mapping, a curve or a region of z plane transform to another curve or a region of w plane. First we have to know that what is isogonal mapping. A mapping is said to be isogonal if two curves in the z plane intersecting at the point z0 at an angle theta are transformed into two corresponding curves in the w plane intersecting at the point w0, which corresponds to z0 at the same angle theta under the mapping. We see the following figure. This is z plane. Here say C1 and C2 are the two curves which intersect at Z0, making an angle theta, and this is UV plane or W plane. Here also two curves C1 dashed and C2 dashed intersect at W0, making the same angle theta. This is called isogonal mapping. Now, conformal mapping. A isogonal mapping W is equal to f of z is equals to u plus iv is said to be conformal if the sense of the rotation as well as the magnitude of the angle is preserved. So in this figure, say it is z plane, C1 C2 making the angle theta at Z0, UV plane or W plane. Here also two curves making same angle theta intersect at W0, and here the sense of rotation and the magnitude of the angle both are same. Okay, so this is called conformal mapping. Now there are some theorems. First, theorem 1 is, if a function fz is analytic and f dash z not equals to 0 in the region D of the z plane, then the mapping W is equals to f of z is conformal at all points of D. The points where f dash z equals to 0 are called the critical points of the mapping. For example, if the function fz is equals to e to the power z, which is analytic everywhere in the finite z plane and f dash z not equals to 0 for all z, so the mapping W is equals to e to the power z is conformal everywhere in the finite z plane. This is first example, and another example is if the function is fz is equals to say 3z square minus 2z plus 1, which is also analytic everywhere in the finite z plane, but if dash z is equals to 6z minus 2 is equals to 0 when z is equals to 1 by 1/3. So the mapping w is equals to 3z square minus 2z plus 1 is conformal everywhere in the finite z plane except at z is equals to 1/3. Hence, z is equals to 1/3 is the critical point of this mapping. Okay, then theorem 2. Let w is equals to f of z be a conformal mapping at z is equals to z0. Then under this mapping the tangent at z is equals to z0 to any curve C1 in the z plane passing through z0 is rotated through an angle argument of f dash z0. Now, some special type of transformation is there. First one is the transformation w is equals to z to the power n, where n is positive integer. Here dw by dz is equals to n into z to the power n minus 1. So dw by dz is equals to 0 at z is equals to 0. Thus, the transformation w is equals to z to the power n is conformal at every point in the finite z plane except at z is equals to 0. So now let w is equals to r e to the power I phi and z is equals to small r e to the power I theta. Then from 1 we have capital R e to the power I phi is equals to small r to the power n into e to the power I n theta. That means from here capital R is equals to small r to the power n and phi is equals to n into theta. This is 2 and this is 3. So from 2 and 3 we can conclude the following facts. Number 1. If R is equals to constant, say C, then capital R is equals to C to the power n. So the circle of radius C about the origin in Z plane is mapped on the circle of radius C to the power n about the origin. And number 2 is from 3 we see that the radial line theta is equals to alpha through the origin in Z plane is transformed to the radial line phi is equals to n into alpha through the origin in the W plane. So the slope of phi lines is n times of the slope of the theta lines, and the circular sector with its vertex at the origin and radius C in Z plane is magnified into circular sector with vertex at the origin and n times the central angle. In the W plane with radius C to the power n. Okay, there are also some factors. Now the second transformation is the transformation W is equals to Z square. In this transformation, this is the particular case of the above transformation, and we can discuss similarly by converting it to the polar coordinate. Here dw by dz is equals to 2z, so dw by dz is equals to 0 at z is equals to 0. Thus the transformation w is equals to z square is conformal everywhere except at z is equals to 0. Now if we let z is equals to x plus iy and w is equals to u plus iv, then w is equals to z square becomes u plus iv is equals to x plus iy whole square. That means u is equals to x square minus y square and v is equals to 2xy. So it is 2 and it is 3 where it is 1. So from 2 and 3 we can conclude the following fact. If x equal to constant, that is equals to a, then u is equals to a square minus y square and v is equals to 2ay. So eliminating y from these two, we have v square is equals to minus 4a square into u minus a square. That means the line x equal to a in the z plane correspond to the parabola v square is equal to minus 4a square into u minus a square in the w plane. And if we replace a by minus a, that means we see the line of x equal to minus a in the z plane, then we get the same parabola in the w plane. Okay, and if we take a stripe between the lines, so this is for x equal to a and this is for x equal to minus a. This is for z plane and w plane, this is the parabola. And if we consider for the stripe, that means the lines for x equals to a and x equals to b, then there also the figure will be this type. Say this is the stripe, say this is x equal to a, it is x equal to b, then in the w plane this is the parabola. Okay, and if we consider the stripe or x equal to minus a and minus b, x equal to minus a and minus b, we get the same parabola as this type. This is for w plane and this is for z plane. Okay, so it can easily see that the both the domain in the z plane to the right of the line the x equals to a, and so the left of the x equal to minus a is corresponding to the exterior of the parabola v square is equal to minus 4a square into u minus 4a square. Okay, so now we illustrate some examples in the next chapter.